All right, today we are doing inductors. This is our seventh class of electromagnetism. So let's go over the homework first. Determine the electric field at a point of a square with the uniform surface charge density sigma, and edge length 1. So does anybody know how to do this? Alvin, were you able to do it? That's fine. I'll just go over it then. So we can use Gauss's law. We can say that integral E dot dA equals Q over epsilon E naught. So basically we have like this square, we have our point. Basically we can construct a cube around this point. So we can turn this into a cube. This cube will have a center at this point, and then one of the faces will be the square that we're given, right? And then we can basically say that the electric field um electric field times the area. Since it's edge length 1, we can just say 1 equals sigma times but also we have to do 1/6, right? Because we have only one face out of 6 for the flux, so it's 1/6. Uh, sorry, wrong 1/6. Here, 1/6 over E naught. So we can say E is sigma over 6 E naught. All right, any questions? If not, we can move to the next problem. A point charge Q is placed at one of the vertices of an imaginary Gaussian cube. Uh, wait, imaginary Gaussian surface, sorry. Find the electric flux through one of the faces of the cube. So, this is very similar to the first problem. Um, we have our um, Gaussian cube. We have our point, right? This is Q. We want to find the electric flux through these faces. So we will deal with the faces separately. We have these three faces which have which have point Q as one of their vertices. And we have like these three opposite faces, which are like they don't have Q as a vertex. So for the faces that are like opposite Q, they don't have Q as a vertex. For those faces, we want to find the flux, right? To find this flux, we can use a similar trick to number one, uh, except now we still want to keep Q at the center of some surface, right? So now we can just construct a cube with center Q that is basically double the side length of the original cube. So basically, we're gonna take our cube, our original cube, and we're gonna place another one here, another one back here. Sorry for the bad diagram. Another one here, and four more on top. So basically now we pretty much just have this Q and we have a bigger cube, specifically double the side length, around it. And now uh we see that the flux, electric flux through the opposite face, through the bigger cube will be Q over E naught. And this is just by Gauss's law, since since we if we just take one of these faces, this face, right? This comprises 1 over 24th of the total surface area of our bigger cube. So we can just say that the electric flux through one of the opposite faces is Q over 24 epsilon naught. All right, so we found the outer faces. Now let's find the faces, like the inner faces, the one that are touching Q. To find these, we can simply like subtract the total electric flux. We can say that our flux, Q over E naught, we can say that our total flux, Q over E naught, minus these three faces we know have flux each of Q over 24 E naught. You can subtract those three, and then since those three interfaces comprise the rest of the flux, we can simply take 1/3 of that for each of them. So we have that this is the flux, the electric flux through each of the interfaces. And we find that this is um 7Q over 24 E naught. Are there any questions about this? If not, we can move to the second problem. The third problem, sorry. Lucas, you want to do this?
Yeah, sure. So, all right, we're given the conducting disk, a radius big R, rotates about a vertical axis through its center, with an angular velocity omega while placed in the uniform magnetic field B in the positive Z direction. Find the potential difference between center and edge of the disk. Okay, so it's always a good idea to draw a diagram. So, say this is going to be our disk over there, and then this is its vertical axis, and then it will go something like that, right? And then, okay, so it's placed in a uniform magnetic field B in the positive Z direction. So everywhere my magnetic field will be pointing upwards. So that'll be my B field that's uniform everywhere in space. Okay, so B, which is in the Z direction. And then let's see. Okay, my disk is spinning at an angular velocity of omega. So it'll be spinning maybe that way. The omega, find the potential difference between the center and the edge of the disk. Okay. So, right, remember how we defined potential, right? So in the case of electric field, like electric potential, right? We said that if we have some potential V, so V, we said let's just do absolute value for now so we don't have to care about the sign. So V would be like some integral of like your electric field vector and then do the dot product with that with some infinitesimal displacement, right? So E dot into ds. And now, and now, okay, how do we use this to find the potential difference between center and the edge of the disk? Well, okay, so think about it. So we have a conductor, it's a conducting disk. What does this mean? It means it has charges in it. So when you have charges in it and they're free to move, right? Like you can have things like currents. So when you have these charges that are like moving with the conducting disk. So, your conducting disk is rotating. That means that there's going to be a Lorentz force because you have charges that are moving and you also have magnetic field. And remember the Lorentz force we had F was equal to uh, or the magnetic force. Okay. F is equal to Q and like V vector. So the velocity vector crosses the magnetic field vector. Okay. So if I look at this point over here, its velocity is pointing sort of into the page. Let me redraw that. So the velocity vector would be pointing this way into the page, and notice it's going to be perpendicular to this B field vector over there, because the magnetic field vector that's pointing in the positive Z direction, while the velocity it's pointing into the page. So, if I call it I set up my coordinate axis as, let's say, uh this will be my Z direction, this is my X direction, and this is my Y direction. Did I know that my velocity of any charge on the conductor as a function of its distance from the axis, from your mechanics days that it was omega and then crosses like the r vector, right? And then here, you'll notice that, velocity is pointing into the page, so it's just equal to omega times r and then in the y cap direction. And so if we do the magnetic force, well, then this would equal to q, and then your velocity would be omega r, and then b over here, the b vector, we can write it as the magnitude of the magnetic field, and then times like the unit vector in the z direction. So we can write q omega r b, and then we do the cross product, right? Y cap crosses z cap. And y cap crosses z cap, these two are all perpendicular to each other and they're unit vectors. So the magnitude of this will be 1. So I do magnitude of f, well, that's just equal to my q omega r and then b. Okay, now this is my magnetic force. We're assuming that I know the problem doesn't say, but for these problems, you would assume that it's like in a steady state, so all charges are under force balance. So if this is the magnetic force and it needs to be under some sort of force balance, that means there needs to be some electric force that keeps it in force balance. And what's electric force? Electric force is Q times E, right? So I can say this is also equal to Q times some electric field. And notice how the Q that cancels, which is pretty nice, meaning that I just get my my E would just equal to omega r times b. And by the way, E is a function of distance from the central axis of the disk. So I'm getting this equation over here. E as a function of r is omega rb. And then, okay, as for the potential difference between the center and edge of the disk, well, now I can just apply this formula I have over here. So that means that, or I'll write it over here. So magnitude of E just equal to the integral of E down to ds. Well, I know that my electric field, wait, how do I know which direction my electric field is? Well, the magnetic force if you use the Lorentz force law, right? So my velocity is pointing into the page, my magnetic field is pointing upwards. So this will be the direction of my magnetic force. And for there to be force balance, I need an electric force pointing to the left, basically radially inwards. So if I want to find the potential difference between the center and the edge of the disk, well, I'll choose this path over here. So I do my integral of e down to ds from here on a path that way. And what does that allow me to do is that because my ds vector will always be pointing radially, and my electric field vector is also going to be pointing radially, then this dot product over here just turns into a simple scalar product because E and ds are in the same direction. So then I can write my integral as from like 0 to r, or from big R to 0, like it doesn't matter because I'm just looking at the magnitude of the potential difference. So potential difference is integral from 0 to big R of E as a function of R times dr, right? Or ds. Right now I'll call it dr. Uh, so omega R B and then dr. And so what will I get? I'll be getting, you do the integral, you'll get omega times big R squared times B and then divided by 2. And that's just the potential difference between the center and the edge of the disk. So that will be our final answer. Yeah. Uh, does that make sense to everyone? If you have any questions, just like shout it out or send a message in the chat. Otherwise, that's the end of the homework review. All right, got it, Alvin. Yeah, that's good. Okay. Sean, do you have any comments to add to for this problem? Or should we move
No.
on?
Yeah.
All right. Okay, let's go on. Yeah.
So yeah, covering inductors today. You can go ahead, Lucas.
Oh, okay. All right, let's talk about inductors today. So, all right, you know, all right, so you know about like I know we didn't really discuss circuits yet, but you probably have a basic understanding of circuits. So it just consists of usually just consists of you have a battery. So this one over here, epsilon, that's our battery over there. And then we have like wires that conduct current, and then you have current that flows from a positive terminal to a negative terminal of the battery. Of course, because electrons have negative charge, uh, they're flowing in the opposite direction of the current. Remember, we learned that in a few weeks ago, but just as a recap, the direction of the current is the direction that positive that it's the direction that positive charges would flow, meaning that it's the opposite of the direction that negative charges will flow. So if the positive charges flow from the positive terminal to negative terminal, in other words, goes this way, then the negative charges would instead be flowing this way, right? From the negative terminal to the positive terminal. That's just a bit of review. So yeah, circuit pieces like resistors, you can add it to the circuit. So for example, here we have a resistor over there. We also have ammeter, and what it is just measures like the current through like some element in the circuit. Also have a voltmeter here, which just measures like potential difference across some element. But yeah, so those are just different elements you can add to a circuit. And yeah, circuit diagram. So for example, this one's just a circuit diagram. Just use it to represent like the battery and wires and the connection of wires and how we attach different elements in our circuit. Yeah. All right. So here's a new circuit element you might have not heard of before. It's called an inductor. Now that name, it might seem a bit familiar to you because last week we learned, or actually 2 weeks ago, we learned about what was called like sort of uh inducing currents, right? We were talking about how if you have like, for example, if I have a wire loop over here and I have a magnetic field that's going through the loop, for example, that way. Now, if my magnetic field is changing and as a result, what's called the magnetic flux is changing. Remember, we defined magnetic flux as the magnetic field and dot onto the area vector. Probably should remember this. This was the magnetic flux, and we said that if I have a changing flux, so if I have d flux over dt, what that does is it creates an sort of like a voltage difference uh across the across the wire loop. I said that was equal to negative epsilon. And you can think of it as like, because of that, there's going to be a current generated in the loop, right? So that was just in inducing a current because when I have the changing flux, it induces an EMF and that causes an induced current. And inductors, they operate on a pretty similar principle to that. So what are inductors? They're just an electrical component in the circuit. Uh, they can store energy. For example, Like that's true for most elements in the circuit. For example, resistors, they'll do something called they'll they'll heat up, so that really dissipates sort of thermal energy from the circuit. But yeah, and inductors, it generates a magnetic field when current flows, and it generates a current when the magnetic field changes. And you know, this probably should seem like it should seem familiar to you because because there's a magnetic field generated through the inductor. When the magnetic field changes, there's going to be your d flux over dt, and then there's going to be the negative epsilon, and that causes a current. Now, inductors, they have special shapes. So a lot of them are in the form of solenoids. So remember, this is what a solenoid is. It's just like a cylinder and you wrap a bunch of wire around it in loops. It can also be what's called a toroid. So remember, this was actually a homework problem from, I think, last week or 2 weeks ago. We were trying to find the magnetic field that goes through the that goes through a toroidal solenoid. So just instead of wrapping my wire around the cylinder, I wrap it around sort of a ring, and that forms, or like a torus, right? And that forms a toroidal solenoid. Yeah. All right. So let's talk about the mechanism for what's called self-inductance. So basically, how do inductors work? Okay. So for example, if I have an inductor over here, which I'll draw as just like a regular cylindrical solenoid, so like that, and then so this is just made of like wire, and I basically just make it like sort of coiled around itself, right? And then I'll just put a current through it. So I'll put a current, oh shoot. So there's a current going through it and it has maybe magnitude I, right? Okay, so remember when we learned like Biot-Savart law and like the first class about magnetism, we said that if we have a wire that carries a current, it generates a magnetic field, right? Remember, if I have a infinite wire like that, a magnetic field will run in circles. And in general, if I have a wire that carries current, I can find the magnetic field produced by it by doing my Biot-Savart law. So remember, yeah, Biot-Savart law, or I can also use what's called the right-hand rule. So the current's going this way. I point my thumb in the direction of the current and I curl my fingers, and the direction my fingers curl will be the direction of the magnetic field, right? And we also learned about solenoids. So, uh, oh, my bad. All right, yeah. So when we had a solenoid, just like how we have here for inductor, I have a solenoid. So this is my solenoid. And then I have like current that runs through it, maybe in this direction. Then what I'll do is I'll curl my fingers in the direction of where the current is going, and then my thumb will point in the direction of magnetic field. So in this case, remember the magnetic field be pointing, it will look something like this. So inside the solenoid, if it's infinite, it will be just like parallel lines going upwards. And then outside the solenoid, uh, there should be no magnetic field. But if it's not an infinite solenoid, remember it looks something like this, right? Yeah. Okay, so if I apply it to my case for an inductor, let me erase this first. So for an inductor over here, what's the magnetic field generated? What does it look like? Well, so the magnetic field would look something like uh, magnetic field would be going through the solenoid that way. And what does that do? Well, okay, there's a flux through through the solenoid, right? Because I have a magnetic field that goes through a solenoid, I have a flux. And so if I have an increasing current, remember that increases the magnetic field. And if I have an increasing magnetic field, I have an increasing flux. If I have an increasing flux, I create an EMF and that creates a current. So just to write that all down, uh, so I have a increasing current. So if I increase the current, what does that do? That increases the magnetic field. If I increase the magnetic field through the solenoid, that increases the flux. And if I have a changing flux, so here I'm increasing the flux, that creates an EMF. And if I have an like I have an increase in EMF, or I just have an EMF, okay. And then what does that do? That causes a change in the current, and it will be decreasing the current. So, for example, I had over here, I increased the current in the beginning, and what does that lead to? You'll eventually find that um because I have the Faraday law that says that d flux over dt, I'll just write it again. So d flux over dt is equal to negative epsilon. Remember, the negative here is really, really important. And what does that mean? It means that if I have for example, an increase in the magnetic flux, there will be an EMF produced that'll lead to a current that reduces the flux. So in other words, it will always try to oppose the change in the flux. What does that mean? Well, if I have an increasing current, I'll have a negative EMF, meaning that what the inductor will try to do is it tries to decrease the current. So you can sort of start thinking about like, what does the inductor really do? Well, what the inductor does is that if I have an increasing current through it, the inductor will behave in such a way so that it will try to decrease the current. And similarly, if I have a current that's going through an inductor and over time it's decreasing, the inductor will behave in such a way so it will work to try to increase the current through it. So yeah, decreasing current causes decreasing magnetic field. Changing magnetic field creates induced EMF, current begins flowing again. And you'll start seeing how like a more quantitative version of how to really express like the mechanism of an inductor and how it really opposes the change in current. So if you really want to understand what inductors are, just remember by having changing just remember this entire chain reaction over here and how increasing the current in the beginning that will ultimately lead to like an, a decrease in the current because the inductor always tries to oppose like a change in current. Yeah. Yeah, we can move on to next one. Wait. Uh yeah. Uh all right. So energy stored in inductor. Yeah. So inductors, wait, give me a second. Oh, okay. All right. Yeah. Yeah. Okay. Energy stored in inductors. So inductors, they can store energy in the magnetic field. Energy. Okay. So how is their energy? Well, you will find that it's related to the amount of current that goes through it, which makes sense, right? Because if you have an increase, like you can think of it as if you have more current, you have more magnetic field, right? And if you have a greater magnetic field, you expect there to be more energy, right? Like that just makes intuitive sense. It's also related to what's called the inductance of the inductor. So inductance is just an intrinsic property of the conductor. So you'll find that of the inductor, right? So you'll find that how do I express the inductance? So the inductance is defined as L, right? So it's equal to the number of loops the like number of loops of the inductor and times the magnetic flux through it and divided by the current. So for example, if I draw the solenoidal inductor over here, so it will just be the number of loops is just the number of these full turns that the solenoid makes. So here it will be like 4, right? Okay. And then, by the way, remember I said that inductance, it's like an intrinsic property to the inductor. And you might be thinking, why do I have, like, if I have magnetic flux divided by current, how is it just an intrinsic property? Like, wouldn't it depend on the current? Well, the thing is that magnetic flux divided by current, this will always stay constant. And, how do I know that? Well, if I have uh a solenoid and it's an inductor, right? So remember how we derived using Ampere's law that the magnetic field inside the solenoid, that's equal to mu zero and then times the number of loops per unit length and then times the current. Well, then what's the flux? Well, flux would be equal to the V and then times the area, right? So flux, or let's just do number of loops times flux, right? Because like that's simple. So just be equal to big N and then times mu zero Ni and then times the area of each loop, right? So times, let's just call it A for now. So the area A. And so what's the inductance? Well, the inductance is this divided by this over here and then divided by the current. Well, so that just equals to the total number of loops times mu zero times the number of loops per unit at length and then times the cross-sectional area of the solenoid. And you can see it doesn't depend on the current that goes through the inductor. It's an intrinsic property of the inductor. Okay, so if you work out the units, you'll find it has units of what's called Henry. It's just some scientists. Yeah, it has units of Tesla, meter square second per Coulomb. So remember, Tesla is the unit of the magnetic field. Meter second, you all know Coulomb is just the units of like some electric charge, right? Sometimes we say, yeah, sometimes remember how we said that n was the small n was equal to number of loops uh per unit length, per length. We can also say that L is just uh L per loop. So if we do that, so L per number of loops, and remember we said number of loops is just the big N, right? So we can cross that out and we can write L over N, and that just equals to mu zero times small n and times the area. This is just deriving some, just it just helps you see like how the inductance, it's an intrinsic property of each inductor. It only depends like for a solenoid inductor, it only depends on uh that cross-sectional area and number of turns and the number of turns per unit length. And you know, mu zero, that's just a constant that scales everything. Yeah. So uh we're gonna later on we're gonna derive what exactly is the energy in an inductor, but here you can get a definition of what's the inductance of an inductor. So it's just defined as big L, and you can find it from doing number of loops times magnetic flux divided by the current. Yeah. Let's go on. If you have any questions, by the way, just let us know in the chat and we'll answer them. Oh, yeah. What is the inductance big L in terms of the constants of the inductor? Uh, yeah, I'll just uh yeah, we can just how about this time? Let's say we have a toroidal solenoid. So last time, like in the previous slide, I did a solenoid that's like it's a solenoid, right? Let's do a toroidal solenoid that acts as an inductor. So instead of a cylindrical solenoid, let's do a toroidal solenoid. So I'll give you guys some time to do it. Yeah. So if you don't remember, the solenoid will look something like oh wait, this is my ring, and then I'll be oh yeah, and I'll be wrapping my wire something like my wire will be wrapped around like that around the solenoid. And then yeah, something like that. Remember it goes in loops, so uh yeah, so remember just to remember like the direction of the magnetic field and remember our definition for inductance L equals to the number of turns and then times the flux and then divided by the current. Yeah, and let the radius just be like R. Yeah. yeah, maybe one more minute to think about this problem and we'll go over it.
Just as a hint, in a way, remember that the magnetic field due to a toroid is mu zero times the number of turns times the current through it over 2 pi r, where r is the radius. If you don't remember how to derive this, you can think about Ampere's law, and you can watch our previous videos on the magnetic field that we covered a couple of classes ago. So I'll give you still a minute or 40 seconds to work on this. I think we can go over this now. Um, so we have this definition that Lucas wrote, L equals number of turns times flux over I. Recall that flux is B times the cross-sectional area. So that we can say that L equals N B A over I, which will equal N times mu zero N I over 2 pi R times cross-sectional area over I. And then this will become L equals mu zero N squared A over 2 pi R. And if you recall so this is for the toroidal. And if you remember the expression for the solenoid, we had mu zero N times little n times a. And you can see that this is like very similar because in a way you can think about the small n, number of turns per length for a toroid, as the number of turns per the length of the circumference, which will be 2 pi r. So in a way these expressions are basically equivalent. Um, yeah, that was like a side note. Any questions about inductance of a toroid? If not, we can move on, right? Oh, go back. All right. Do you have a question?
Yeah, and let's just quickly go over how do we really quantify the voltage across an inductor. So we'll define the voltage across an inductor as L times di over dt. So L uh L di over dt. And then, so that's just the magnitude of the voltage drop. So how do you really know the sign, right? So if the, so okay, remember how we talked about when we have an inductor, it'll always like serve to oppose the change in current. So if I have an increasing current, I'd expect the inductor to create a voltage drop, right? Because if I have a voltage drop, that in like okay, you can think of a voltage drop as increasing the resistance, right? Because if I have like just a simple case of a battery and then I have a resistor, if I have a bigger resistor, what does that do? Well, if I have a bigger resistor, so higher R would mean that there will be a smaller or right. Higher R would mean that we need a smaller current, right? Because you have the same voltage drop across this battery. And so because, like V equals IR, you probably have learned this before. It's okay if you haven't. We'll go over it next week. But if we have a higher resistance, then we'll have a smaller current, right? And similar to this, if I have a increase in the current, the inductor will try to oppose this increase of current by decreasing the current. So if I make the voltage drop, so if I have a voltage drop across the inductor, that'll mean that will serve to decrease the current because it's basically just like I'm increasing the resistance in a way. So remember, the sign of it will just be if current's increasing, I have a voltage drop. So if I dot, which is just di over dt, if I dot is greater than 0, then I'll have a voltage drop. Okay. If I dot is less than 0, I dot less than 0, then I'll have a voltage rise. Because if I have a voltage rise, it will help increase the current when the current's like decreasing. So just remember the mechanism for a current for an inductor to operate, and that way you can just always reconstruct and judge what to what like will the voltage be like a rise or a drop. Okay. So yeah, that's just quick overview of voltage across an inductor. Yeah, let's move on. Yeah, so using the fact that the power generated by an inductor is I times the I times like voltage, so like current times the voltage across it. What's the energy in an inductor? Yeah, so give you guys a few minutes to do that, and just remember the power. How do we define power? Power is just equal to the d energy divided by dt. So just if we're given what's P, so current times V, find what V is, find what I is, and do the integral, and then you can find E. So I'll give you guys a few minutes to do that, and we'll go over it. And just as a reminder, remember we had, what was the V? V was equal to the inductance times the D current over dt. So dI over dt. Right. Let's go over this. Uh, yeah, shall we? Uh, yeah. Okay. Shall we? Do you want to go over this one?
You can go over it.
All right, sure. Okay, so all right, we have P equals d over dt. Okay, so what do we have for power? We're given power is equal to I times V, right? So we have current, okay, current times V voltage drop equals to power. All right. Remember what we said for voltage drop? Voltage drop is equal to L times di over dt. So this also equals to L times I, then di over dt. And we also have our definition for power, right? Power equals to dE over dt. And then, okay, you can see that dt, it cancels from both sides. So we're just left with Li di equals to dE. What does this mean? Well, if I integrate both sides, then, okay, I'll integrate dE. dE is equal to, or integral of dE is equal to integral of Li and then di. Well, okay, this might seem, you might think that we can't find integral of Li di, but if you think of I as just a variable, and we have d of that variable, it's just like, it's the same as doing integral of x dx, because I here is just a dummy variable. Like, we can name it anything else. We can also name it like a or b or whatever, but this integral is just equal to Li squared over 2 and then, plus some constant, right? And then obviously this side will just become the energy. And because we're saying that we'll define the energy in an inductor as a potential energy, and potential energy, like you can choose an arbitrary like 0 0.4 for the potential energy. So what I'll choose is that I'll choose that when the current is equal to 0, it stores 0 potential energy, meaning that I can just say that the energy stored in an inductor is simply the inductance times the current through it squared and then divided by 2. So this will just be my final answer for the energy in an inductor. And just overview recap of the derivation is just remember your definition for power is just d over dt. And then we define power as also equal to current times the voltage drop. And just remember what we define as the voltage drop across an inductor, and it just ends up being an integral, and you can find the potential energy. So yeah, that's just the energy in an inductor. Any questions about it? All right, if not, let's move on. All right, yeah. So what is the energy density of a magnetic field? Consider the energy in an inductor. Uh, this will be I'll give you guys some time to attempt this, but it will be a kind of difficult derivation, but I'll let you guys attempt it and we can go over it together. So, just some hints. Yeah. So obviously, to actually prove like generally what's the energy of a magnetic field, that's pretty hard. So for now, let's just prove using an inductor what we know for the energy, and then like we'll try to prove what's the energy density of the magnetic field. So, just as a reminder, we have that like we'll just define energy density as E equals to we'll say it's equal to dB, and then, or sorry, oh, shoot, my bad. Okay, the energy density, so rho E would just equal to say d E divided by uh d volume. Or to not confuse the E with the electric field, let's just call it U because it's a potential energy anyways. So uh energy density rho U would be equal to du over dV. So yeah. And remember what we got for an inductor. So U of an inductor, that's equal to L I squared and then divided by 2. Yeah. So try to go from there. Oh yeah, and remember what we defined for inductance. So L, remember L would equal to uh N times phi divided by the current. Yeah. I'll give you guys a few minutes. Yeah, don't be discouraged if you can't do it. So we'll go over it together.
This is volume, by the way. Don't mix it up with voltage. Yeah.
Yeah, yeah. You can also write it as just like potential energy per volume, but yeah, if we're saying that the potential energy everywhere is constant. So yeah, try going from there and yeah, take a few minutes. All right, how about I'll give you guys maybe another minute to do it. It's a bit tricky, so yeah, I'll give you guys a bit more time. Let's try doing this. Okay, so all right, might need some extra space, but okay, it's fine. So all right, we know that. All right, we want to find uh, we want to find U, right? So let's just go from the power formula we got. So remember we had du over dt, right? D over dt, that was our power. We got that was equal to I times V, right? Oops. And that's equal to current times I times your voltage drop. Well, okay, you know what your I is, right? You can write I from this formula over here. You can say that from this, I would equal to N phi and then divided by L, right? Now, yeah, so we can plug that in. Now for V, well, remember how we had that Faraday's law, right? In Faraday's law, we had V would equal to, or basically your epsilon, right? That's like your d phi over dt, right? So d phi over dt and times, yeah, d phi over dt and then times the number of loops, right? Or some people, they put like number of loops in the phi, but yeah, let's just call it d phi over dt for now. So this is equal to, what will this equal to? Well, this will equal to n times phi divided by L, and then times your d phi over dt, right? And then if I cancel the dt from both sides and I do the integral, then I'll get that u would be equal to big N phi squared divided by L, right? Okay, now actually, actually, let's do, we need to call that, well, V equals yeah, yeah. This should be B equals that. So should be here. So yeah, it'll actually be n squared over here. N squared phi squared divided by L, I think. Yeah. So that's our U. And then actually divide by 2L, right? Yeah. And now we want to write inductance, right? Well, inductance L, what do we say it was? L was equal to your big N and then times your flux divided by I, right? Now we know that flux, that's B times the area. So that will be equal to your, I believe, mu zero I times small n, and then times mu zero I small n times area, right? Because it's the flux, and then divided by your I. Oh, and also times the big N. So this one cancels. And what is this equal to? Well, this will also equal to mu zero, uh, or there's no I, right? You can also write yeah, you can write small n as big N over L, right? So mu zero A times big N squared, and then divide by the total length of the solenoid, right? So if I plug that in here, I'll be getting equals to uh oh, and also I can also plug this in, so phi would equal to uh wait, this will be n phi over I. Yeah. So this is what we're getting for inductance, and we also have uh right. So I'll get n squared and times my phi squared, which will be mu zero times hmm, n squared mu zero squared I squared n squared a squared, right? And then and times big N squared, and then divided by 2 times your mu zero a n squared divided by L, right? And then yeah, yeah, okay. And then notice this cancels here, and we'll get canceling of one of the mu zeros. And after that, we can write, okay, this one of the a's also cancels. So we'll be getting equals to, if we clean it up a bit, mu zero times I squared, and then times small n squared, and times your a, and divide by, I think there should be an L over here. Right, right. Yes, this is looking correct. Yes. And then okay, we're getting this for our remember this is still equal to your energy. And you also have again B equals to mu zero times I times small n if we're considering a cylindrical solenoid. So if we know that, then we know that okay, uh A times L, right? That's equal to volume. So this will just equal to, if I do the B squared, remember, B squared, if I do B squared, so B squared would be equal to mu zero squared, I squared, and then times small n squared. So, I have an extra mu zero here if I do the b squared. So I first have to divide by mu zero, right? So b squared divided by mu zero, I'll be getting mu zero I squared n squared. And then so times a times this, a times L, that's equal to the volume V. So I'll just call it volume, times volume, and then divided by 2, right? So what am I getting here? So I'm getting the total energy U, that's equal to B squared divided by 2 mu 0, 2 mu 0, and then times your volume. So what does that mean? Well, that means that my potential energy per volume, so basically the energy density of the magnetic field equals to rho u b, I'll call that. That'll just equal to b squared divided by 2 mu 0. And you can see it's a really simple expression that we got from like a lot of messy math that we did with the energy of an inductor. So, you know, the derivation was messy, but the final result we got was really, really nice and clean. And it turns out, sorry, it turns out that even though like our derivation was just for an inductor, this formula for the energy density of a magnetic field, it's true for all magnetic fields, not just the magnetic field created by an inductor, okay? In general, the energy density of a magnetic field, you can always write it as the magnitude of the magnetic field squared and divided by 2 mu 0. And it's a pretty important identity that you should be familiar with. So yeah, that was a really messy derivation, but you can see we got a pretty nice result and it was pretty clean in the end. So yeah, don't worry if you didn't understand it, but uh like try to understand it after this class, but like the most important thing to remember is just the result we got, which is the energy density is b squared divided by 2 mu 0. And that's like, it's a really famous identity and you should know it well. So yeah.
Yeah, and as a side note, this is related to the energy density of an electric field, which is in case you're curious. This is the electric field and this is the permittivity constant, E naught. Anyways, yeah.
Yeah, we can actually prove that. I believe we can also prove that by, I don't know if we already did it, but you can prove it by like considering the energy stored in a capacitor instead of an inductor. Uh, Remember the energy in the capacitor was CV squared over 2. Uh, we can go over that later if you guys want, but yeah, just remember electric field energy density and magnetic field energy density. Yeah, pretty important. All right, let's go on then. Okay, so here are some examples. First one, for a solenoid with inductance L, a current given by IT equals AT squared, where A is a constant. How much energy does the magnetic field gain in 8 seconds? Also, what is the magnetic field in the solenoid? Yeah, maybe a few minutes to do this. And just some important things to remember. U, oops, U equals to L I squared divided by 2. And you also have that uh rho b equals to your b squared and divided by 2 mu 0. Yeah, so maybe a few minutes to do this and we'll go over it. All right, let's go over this. Sean, do you want to do it?
Yeah, sure. So we have, right, so we have u equals 1/2 Li squared. So as a function of t, u of t equals 1/2 L. I of t is at squared, so we can write a squared t to the 4. At 8 seconds, the energy u of 8, you can calculate it. 8 to the 4 is like 2 to the 12, 2 to 11. So you have 2048 L A squared. And u of 0 is obviously 0. So it gains this much energy in 8 seconds. Yeah, so mainly just knowing how to use 1/2 Li squared. Any questions on that? I'm not getting anything. All right. Magnetic field in solenoid. Um, this is very simple. B equals mu 0 Ni. Uh, yeah. Any questions? Not. We can move on to mutual inductance. So, mutual inductance is basically where you have two solenoids, and what you have a current, so we can use this diagram. You have coil 1. You have a current flowing through solenoid 1, and this creates a magnetic field, right? Because B equals mu 0 Ni, you have a magnetic field. This magnetic field will encompass space. It'll reach the second solenoid over here. See, it's reaching your second solenoid. By Faraday's law, this will induce a current in solenoid 2. This will induce a current. So this whole process is like it's called mutual inductance. You have a you have two solenoids, you run a current through one, it generates a current in the second one. This has many practical applications as we'll see later. Um, so how to like mathematically how this works, um you have a current I1 flowing through solenoid 1. This generates a B1. All right. This reaches solenoid 2. This makes a magnetic flux through coil 2. This induced EMF by Faraday's law is E equals negative differential of flux is negative dt of BA, right? B1 and A2 of the second solenoid. And then we can see that the rate of change of the flux in coil 2 is some m, which is like our proportionality constant for mutual inductance, times di1 dt, right? You can get that. And then, so we can basically get an expression for m. So this expression for m, as we also see here, is how we define mutual inductance. It's the flux, which is through the second solenoid, which is N2 times B times A, is our flux, over the I1 from the current you're running through solenoid 1. Um, any questions about that? All right. If not, I'll move on. So, the practical application I was talking about is transformers. In transformers, we have our first solenoid over here. We can like, this is the primary solenoid. And we have our secondary solenoid. It's like we're winding a coil around it, right? And if we run a current through this from earlier, the previous slide, we know that there'll be a current in this one, IS. So in this way, we can like we can change our first voltage in the first solenoid, across the first solenoid, sorry, to a second voltage. And this leads to like step up or step down transformers, where like depending on the number of turns um in each solenoid, you can either step up or step down. So if this solenoid had the second solenoid had more turns, you'd create a larger voltage, while if your second solenoid had a less number of turns than the first one, you'd create a less voltage. So this is like a step up or step down. And yeah, to carry the magnetic flux, you usually would use like a ferromagnetic core, is what it's called. Is like you can just like some like um iron, something like that. And yeah, I think that is all. Any questions on transformers? You'll see transformers outside your house on like poles and stuff. They use it a lot to make the power supply for the houses and electrical grid. Yeah. All right. I think that's the end of class also. So if nobody has any questions, we can dismiss class.
Yeah, thank you for coming, everyone. Yeah, see you next week.